So again, I introduced myself geographically, reminded people about the lectures and the times for the lectures, gave you some references, and again, I draw your attention to these particular references. So sorry, are you recording now?
Yes, there's recording right now.
Very good, okay. So we talked a little bit about these references, and I sort of urged people to look at these references. Again, there's many references out there. I'm going to talk a little bit about that later. We talked about our fabrication, the record and the replay. And I gave you some examples of art holograms. And the first thing that I came to here, and we're going to be mentioning this a couple more times, is this idea of the plane wave and the mathematical definition of the plane wave, which is going to pop up over and over again, and representations of plane waves, because they're pretty central to what we're going to be talking about. I then gave an introduction to holography and just fairly generic terms, the way people would have talked about it, and a little bit of the history about Denis Gabor. And I was looking at the video from the last talk, and I'm afraid on several occasions I referred to Denis Gabor as Denisuk. So I apologize about that. They're too close together. And then we talked about the off-axis replay, and we did some mathematics, and we came along and we discussed this holographic principle, where essentially we talked about this idea of producing, when we replay multiple beams, but that one of those beams had the full information about the actual field that we'd recorded. So it's almost like magic. Yeah, we have replayed this recording of an intensity distribution, and we've reproduced an amplitude and a phase. So I think that that deserves the title of magic. So anyways, we talked about the virtual image, again, the geometries, which is something very good to get clear in our head, and of course, the pivotal contributions of Denisuk. And this is one of the reasons I'm extremely proud to be here talking to you today, because of course, I would have read a lot about Denisuk and his work. And of course, ITMO has very, very close relationship with Denisuk. He worked for many years, and some of his original work was done in ITMO. So this is really interesting for me. And of course, we have then the rainbow hologram produced by Benton from MIT. I then emphasized this notion of producing plane wave gratings using two interference beams, and the idea of being able to probe that grating while it's being formed, and not just so during the recording and after the recording, and also being able to rotate the hologram in place while it's being replayed, and being able to find out the variation of the diffraction order as a function of the input angle, using wavelength, for example, to which the dye in the plate is not sensitive. So again, this is going to be quite central to many of the things we're going to talk about. And we talked about on-Bragg replay, and we talked about slanted gratings. And again, I give you a little taster here. Just this is sort of where we're going to be going, where we're going to be looking at diffraction efficiency for on-Bragg replay, or diffraction selectivity for on-Bragg replay. And then we're also going to be looking at the diffraction efficiency as a function of the angle of incidence primarily, but we can also look at it as a function of the replay wavelength. And I introduced this idea of the Ewald diagram in phase space, where in space we have the axes in meters, and here we have the axes in 1/meters in spatial frequency. To find our notation, looked at this from a bigger picture, the general different types of applications you can see here. And again, I always feel a bit worried because it's so shallow in some ways what we're doing here. But again, you can go to those references I gave you. And as I said, at least 3 out of those 4 are easily available to you. And then I sort of told you what I was going to try and do in the next few slides. So again, our plane wave, our interference pattern, and then just this notion again about the representations of the field, that we have 2 plane waves interfering to give this sinusoidal pattern. And then we can take that and we can also represent it as 2 spots in the spatial frequency domain. And that both representations, if we've got our amplitudes and phase, are equally valid. Then we went back, if you'd like, to first principles and just try to remind ourselves what diffraction was and what these other things are. And again, I'm sure you all know this, but I think it's always good just to state them. And then again, I came back and in the context of diffraction gratings, talked about representations of the field in space and its power spectral density and as this Ewald diagram. And hopefully it sort of gave you this idea about the grating equation. We derived out the grating equation, that it told you information about directions, but didn't tell you anything about intensities. But these types of representations, they jump between them. So it's quite a good idea for you guys to understand or to see these representations and be able to deal with these representations. And we came along and we talked about our Bragg selectivity. And again, we have our evil representation. And this idea that we have particular directions where we get this constructive interference in 2D. And again, we derived that. And we talked about it in relation to volume holograms, as opposed to just crystals. And we talked about the fact that we can have multiple Bragg replay conditions for a single grating. So without changing the grating, we can still achieve, or we can still have this Bragg condition satisfied. And again, we try to illustrate that clearly. And that's where we finished the last day. So now, I'm assuming now everybody who wants to attend is going to be here. Is that fairly accurate? Is everybody here who wants to be here? Or who's going to be here? So I can go and do new material? Are we okay? Okay.
Yes, I think it's time to start anyway.
Okay, very good. Okay, now, the first thing is, and I honestly mean this, that it makes things much more interesting for you if you go away, for example, to Wikipedia, okay? I have a great belief in Wikipedia, and I donate money to them every so often because I think it's quite wonderful. When I was growing up, you had to go to a library, and most local libraries didn't have a lot of information. So I think in terms of general information, it's quite good. And a lot of the times it's quite reliable. And I think most of the text about the holography is quite good in there. And of course, they have photographs of people, and they have pictures of experiments, and even some video. So it's really good to look these things up. You can gather a lot of general information, which makes it much more interesting. Historically, there's a couple of characters we should mention in relation to the development of holography. And one of them is this incredible person called Gabriel Lippmann, who won the Nobel Prize in 1908. And he won it for a thing called a true color photograph, but he also worked on microlens arrays, lenticles for integral imaging. So he's quite a hero of mine, himself and Fresnel, quite remarkable people. And he actually recorded interference patterns using broadband white light sources and achieved the recording of color, true color. So most color that's recorded now is red, green, blue. He actually recorded the interference patterns of white light, which is a very short coherence length, and he did this in a really remarkable way. And there are still some of his color photographs out there, but they only managed to reproduce his results about 20 years ago. They couldn't reproduce his results because he had a very, very clever material that was highly sensitive, very fine-grained. So I certainly advise you to go off and read about Gabriel Lippmann and see how this ties in with some of the things we're talking about. Another pair of people that are very interested to read about are Lawrence Bragg and William Henry Bragg. And of course, they worked on X-rays, and they talk about things like kinetic scatter, X-ray kinetic scatter, or inelastic scatter, they refer to. And I know some of you are quite interested in these notions or applications of scatter. Finally, Gabor published a paper in 1948, and you can get that on the web. And he won the Nobel Prize in 1971. So next year is the 50th anniversary of his Nobel Prize. And in 62, Denisuk and Leith and Uputniks did their work on holography, which basically directly led to Gabor winning the prize. So again, we noticed that we're coming up to the 60th anniversary of their work. So these are going to be quite exciting couple of years, I think, in the area of holography. And I really strongly recommend you go out and read up about holography. There's lots of interesting stuff out there, very many resources. Now, the other thing, and I do this sort of to stimulate you guys, because it's quite interesting. But I gave you this slide at the very beginning, and I said that, I'm going to tell you a little story maybe at the beginning of every lecture about things that are maybe related to optics or related to holography. And I want to talk a little bit about a project we actually did with Intel. You think of Intel make computers, but one of the things they're very interested in is the uses that these computers are put to, and they have very, very high speed, very powerful computers. And one of the things they were interested in trying to do was use that computing power to process digital holograms. So in contrast to what we're talking about, in a digital hologram, you basically have a setup, there's various setups. Here would be an inline setup, which would be like the one that Denisuk actually used, where you have a laser, and you illuminate an object. And in this case, the object we have here are 3 slides, 3 microscope slides. And in the layers between the microscope slides, there are tiny little plastic balls, latex balls. And these latex balls are about 10 microns in diameter. And the slides are 1 millimeter thick. The one in the middle will be 1 millimeter thick. And so what happens is we record the intensity at the camera of the light that passes through this layer of glass, balls, glass, balls, glass. And then we process that information, and we process it using computer algorithms. So we grab an intensity here, and the interference here is produced by the light that goes straight through this very weakly scattering object and the light that is scattered by that object. And we can actually come up with images that look like this, where from that image that we capture with the camera, we can distinguish out individual latex balls, and we can, inside the computer, propagate the light inside the computer using effectively the Fresnel transform, and we can find the images of the balls which are 1 millimeter away. So that's quite a large depth of field here. This was implemented in the, I think it was in the red, okay? And the algorithms basically involve iterative phase retrieval algorithms, where you capture images and you constrain them inside the computer, and you extract out the complex field at the camera, and then you propagate that complex field inside the computer to move back and forth between these different planes by doing a Fresnel transform, which is equivalent of a 1 millimeter propagation. Now, digital holography, it turns out, is what we've referred to as 2.5 dimensional imaging, because, for example, in confocal imaging, you actually produce an image of this plane and an image of this plane, and they both have the same resolution. In digital holography, you've actually got different resolutions in the different planes. But it's quite remarkable when you think that using algorithms, and there's a whole range of algorithms, the Saxton-Gershberg, hybrid input-output, error reduction, okay? FineUp would be the man in the area. But you can use this holographic principle, which we talked about in the last lecture, and some clever numerical tricks to actually get out amplitude and phase information at different distances away from the actual plane where the objects are formed. Okay, now back to the hard work. That was fun. So now back to the hard work. Modeling optical scatter and diffraction. So as I said, I'm going to start off by couching this description of holography in terms of these models. So everything we've done so far, you could probably pick up in Wikipedia, yeah? But generally in Wikipedia, if you go and look at the lists of references they give, and most of those references, they don't have references dealing with electromagnetic problems, certainly not rigorous descriptions. And that's what we're going to do here, because we need to do that if we're going to organize the scatter by these holograms, the diffraction by these holograms, and if we're then going to go away and talk about the material properties of these materials, for example, like photopolymers. And we start here with the most complicated series of models, Maxwell's equations, and the requirement to phase match the boundary conditions, your tangential E and H field, in order to figure out what's going in and out. And in general, we're going to be talking here about cosinusoidal materials and volumes with relatively weak modulations. And we might be talking about multiple grating harmonics with some phase relationship with respect to one another or different slants. But there's a whole range of other work to do with surface relief gratings, where you've got very strong edges, okay? Where, for example, you have a surface relief structure like a pyramid, with the pyramid is made out of glass with an index 1.5, and in between these periodic pyramids, you've got air. And you may, in fact, even take these pyramids and coat them with metal, okay? So in those cases, weak modulation can't be assumed, and many of these models I'm going to talk about, I'm going to specifically talk about coupled wave models and a little bit about modal models, they don't work very well. But happily, there's a whole range of different diffractive optical models that have been produced over the years for dealing with those particular cases. And this is something you tend to find, that you have to get that, you have to suit or fit the model to the actual problem. And trying to solve a general problem electromagnetically, most of these methods, if you retain an infinite number of modes, yeah, or if you do very clever numerical tricks, you can get them to converge. But there are some that are much more easy to use, much more accessible, and often they have they provide a better physical understanding to what's happening inside. And that's kind of what we're trying to look for here. In any case, the solution of Maxwell's equations, there's many ways: finite time domain, finite time difference, etc. But numerical solutions, physically valid, but that tends to be slow. Even with the advances now in computer programs and in the software, these still tend to be slow. You get a quantitative prediction, but you don't necessarily get physical insight. And you can have convergence issues for more complex DOEs. If you think it's the convergence of a Fourier series and then another layer of complexity put on top of that. And especially when you go to the TM polarization, or you talk about conical diffraction, where you're not incident in the plane of the grating, yeah? Or when you talk about, as I said, things like very lossy structures, okay? Gratings made out of gold or real metals, then you tend to have problems. You have intermediate models. So you typically, in this case, would neglect higher order field components. So you you take a finite expansion. Now, even in the numerical case, you typically have a finite expansion of the E field. It may be that your approximation in terms of a grid is the way you have this finite situation. Or in our case, we have a finite number of plane waves. But typically in these, you're going to have a reduced number of orders or field components or plane waves or modes, and you're going to have some simplification of the boundary conditions. And there's several ways you can simplify. One is you can simply ignore the boundary conditions completely. The other way is you could introduce some Fresnel reflection coefficients, but you don't actually go ahead and match your E fields inside and outside. So this can produce, in some cases, analytic solutions in particular cases. Once you go above, for example, 4 modes or 4 waves, typically you then have to go and find some way to numerically find eigenvalues, things like this. But they're less physically valid. They're, however, faster, and they have a range of quantitative accuracy, and they give you some physical insight. Now, quantitative accuracy is the eye of the beholder. And what I mean by that is that if you have an experiment that's a very noisy experiment, so you've got random processes leading to noise in the system, then having very, very, very accurate models may not be to your advantage. You may be trying very hard with diminishing returns. On the other hand, typically what you want to do is you want to have a rigorous model that certainly works in some cases, and then you can run your approximate models and compare them to the predictions of the rigorous model, so you get a feeling of how accurate you are. This is quite important. However, I just note here in relation to the rigorous models that because of their difficulty in converging, especially, as I said, for very complicated cases. So for example, imagine you have a non-periodic structure. You may approximate the non-periodic structure by locally periodic structures. And as long as the variation is adiabatic, is very slow, you can sort of stitch the results together to get a feeling for what's happening. And again, that involves approximations and estimations. At the end of the day, your experiment is the arbitrator, ultimately. And if your model predicts things and then you can experimentally verify them, then your model is a good model. Scalar models. You neglect all vector field effects, so polarization doesn't come into this, and you neglect all multiple scatter effects. So you're down to this weak grating in which the light passes through, and some of the light is scattered, but the scattered light is not rescattered. Okay. And typically these provide good qualitative insight, and they can be very fast. And for example, we mentioned above this iterative phase extraction method, iterative phase retrieval, iterative techniques. Often those techniques and the performance of those techniques, you may wish to use a rigorous model with them. But the point is that you want to have a starting point to any search you perform. And these sort of scalar models can sometimes give you a reasonable starting point. You have to be careful when you use them. They're not always going to give accurate predictions. So part of the game is to know when they're valid. And again, you can compare them with the rigorous models for particular cases. But if you're using some sort of a search method, often these things can provide you with good physical insight and a good starting point. Now, this is a figure that I really, really like. And it comes from that Gaylord paper that I gave to you above. And it's been reproduced a number of times. Certainly Moram and Gaylor themselves have put it in 1 or 2 papers. And essentially what you've got down here is you've got the simplest models, and then you work up here to your more complicated models. So the rigorous model is up here, and I just mentioned 2. They're both differential methods. The rigorous coupled wave methods use the plane waves to describe the field inside the planar grating. The rigorous modal method use modes or eigenfunctions, exact solutions, so modes that only accumulate phase as they propagate through the periodic structure. And there have been 2 wave modal or 2 mode modal methods produced. I'm not going to talk a lot about that. Again, you can look in Sims. There's a lot of work there in that area. And in many ways, this is a very elegant approach, okay? because you can treat each one of the modes that you use here has been made up of an infinite number of plane waves. So in that sense, this is a very physical approach, okay? The rigorous modal method has the advantage of the fact that you have plane waves outside the grating in free space. And so I won't say it simplifies, because you have to phase match the field inside the laminar grating to the field outside the grating, but many people are very comfortable with plane waves. And so it has that advantage of a perceived similarity to what people are used to. And also, we typically assume that we have a weak modulation. And in the case of the weak modulation, in some sense, we have a perturbation of the plane waves, yeah, as we're going to discuss. So that's the top end. At the bottom end, we have this transmittance theory that I mentioned the last day, where we've got this something which describes our grating. Is there a question? Is everything okay? So,
Professor Sheridan, there
yes,
is
please.
a question in the chat.
Yeah, please. Go ahead. Ask me.
So what is the physical meaning of neglecting higher order field components? In other words, when are these components important in holography?
Okay, so again, we're going to talk about that later, but essentially we have a coupling. We have a coupling of energy from the input beam to the diffraction orders, yeah, to the orders inside the layer. And if we have a very weak grating with a very big period or a very, very weak modulation, what's going to happen is that we can have a lot of the light scattered into higher orders. So the field inside the volume, in order to represent it, we need a lot of plane waves, okay? So the higher orders will contain energy. And we're going to start out by looking at situations where we only need two orders, two plane waves inside the volume to describe what happens. Ultimately, what happens is that if you only use very few waves, you're assuming that the amount of power in the higher waves is negligible. We don't need the higher waves in order to properly or accurately describe the electromagnetic field inside the volume. Okay? Does that help?
So we hope that yes, thank you for the answer.
Now I'll talk about this a little bit more as we go forward, and we're going to explore the assumptions and the meaning of these assumptions. But ultimately what it means is if we have a sinusoidal grating, we're going to get scatter, and we're going to get scatter on the evil diagram by that amount k, the grating vector. And if we've got power into the other higher orders, typically that means we have to scatter by k to get to the first order, and then from the first order we have to scatter by k again to get to the second order. So that coupling inside the volume requires multiple scatter in order to get to the higher orders. The diffraction orders outside are simply produced by the periodicity of the surface, but it doesn't tell us anything about the actual amount of light in those orders. So again, we're going to talk about this, and hopefully it'll become clearer. So we have these simple models based on this transmittance function where we basically assume that our diffractor is infinitely thin, and we can describe the effects of the diffraction volume or layer by simply dividing the output field by the input field. And so we multiply the input field by a transmittance function to get the output field. And you can see we're sort of just with this multiplication effect is simply, and the multiplication can be on the amplitude or the phase of the input beam. It's a simple single multiplication. So we're effectively assuming at every point we have one effect happening to that field. Now we have two routes here. One route is to Raman-Nath, where we have multiple waves. And we're going to talk a little bit about this, but not a huge amount. But again, the minute we go up from this level, this has no selectivity. If we change our wavelength or angle, nothing happens. And in the Raman case, the effects of selectivity are very, very minor. Yeah, they're very minor. They're mostly to do with direction. But what we're going to follow is this path. We're going to go to Kogelnik. And in Kogelnik, we're going to assume that we have no boundary conditions applied, certainly no rigorous boundary conditions applied, and we only retain two waves. And then we can come back up to this model here, these models, multi-wave and two-wave, and then further up to the rigorous models. So this is a hierarchy where we get more complicated as we move up this path. And this is going to be the path that I follow. And again, you can read more about these other models in the books and the references I gave you, but I will talk a little bit about them. Now, I want to first of all talk about this complex transmittance idea, because it's quite fundamental and it's what people use for a long, long time. And again, it brings out the differences between these physical models and ties together some ideas you might have met in other places. For example, in the area of optical signal processing, where you're using the Fourier transform to describe what are the effects of weakly scattering objects or single scattering objects. So we assume, for example, that we have a periodic variation, and we assume the period in x of that periodic variation is much, much bigger than the wavelength. And typically that means at least an order of magnitude. So 10 times the wavelength or 20 times the wavelength. So big, yeah? So if we have a wavelength here, which is half a micron, we'd have something here which is 10 microns or bigger. And since the kx is 2 pi divided by the period, and beta is 2 pi divided by the wavelength, if the period is much bigger than the wavelength, the grating vector is much less than beta, 2 pi over the wavelength. And again, we just recall that the evil circle that we drew, it had a radius which was equal to beta. It had a radius which was equal to beta. It was 2 pi divided by the wavelength, and that wavelength will be the average, the effective wavelength in that area, in that medium. So it'll be the wavelength divided by the average refractive index in the medium. Okay, so this is our assumption, big, big periods. But we're also assuming that we have relatively weak modulation. Okay, so we have a variation in the refractive index, and we might even go so far as to say, well, the optical path in passing through the object is going to be less than pi or 2 pi. So if we have the thickness of this whatever layer we have, and we multiply it by the biggest variation in the refractive index, we're probably expecting something like pi or 2 pi. So here's our diagram. And again, this will be a diagram you'll be more used to seeing in optical signal processing. We have some rectangular window, and it's in the X and the Y plane, and it has some extent in X and some extent in Y. And then we have some variation in here. And we could imagine it as some glass, and the glass might have some loss, some absorption at different points. The absorption would vary, and it might also have some variations in density. So the optical path going through at different points might change. So when we put a field in here, the field we get out is going to be its amplitude and its phase can be modulated at every point. And we can describe our window, our transmittance function, as the output field. We've got Z0 plus divided by the input field at Z is equal to 0 minus. We've assumed this thing is infinitely thin. And if we just have a rectangular window, then this is going to be a rectangular function. It's going to be 1 inside the window and 0 outside the window. And typically this is going to be the biggest sized thing here. And since it's the biggest sized thing, this rectangle, if we take the Fourier transform of this, for example, we're going to end up with something that's very small or narrow in the frequency domain. Now, we can describe the transmittance function, the effect of this window, whatever this window does. And again, as I said, it could have different amplitudes and phases at every point inside here, in which case this transmittance function will be a rectangular function multiplied by that. But we can describe the effects of this transmittance function, and I do it here only as a function of x, purely for simplicity, as component values multiplied by these phase terms, these Fresnel exponential terms. And we have here a fundamental period, which is pi x, and the fundamental spatial frequency component of that grating, which is kx. And so we write it as a sum of these terms where this m is an integer. And of course, again, we could assume we have an infinite number of values here. And if this is a rectangular function, this would be then equivalent to a rectangular function. We'd have a series of Fourier components, and it could be m plus or minus infinity. So the resulting output field can also be written in exactly the same way. And if we have a unit beam, a unit amplitude plane wave incident on this rectangular function, then basically the output is going to be equal to the transmittance function multiplied by that unit value plane wave. And so we can simply say that the output field here, which can be written in this way, and we've used L here, and L is an integer, but just to differentiate the two things. But it turns out we can show, because we can show that the output is simply the transmittance multiplied by the input. And if the input is 1, then there's you can equate the output to the input. And therefore we can write the coefficients, the components of the field that come out just after this, as being equal to the components of the actual object, the transmittance function. And so it's a Fourier transform. we perform a Fourier transform. There should be a dx here, I'm sorry. Yeah? Okay. We have amplitude components. Okay. So there should be a dx here. We integrate with respect to dx. Now, once we have those components, once we have those plane waves, we have the complex field here. Typically, we want to see what that complex field becomes some distance away. Okay? Some distance away. And if we assume we're looking at it a very far distance away, yeah, we can have our input field at z is equal to 0 and an output field here at z is equal to 1. So this now is the output field over at this plane of distance z is equal to z prime away. And we can say our output intensity is going to be the magnitude of that squared. And we've described the output field here as an angular spectrum, as a set of plane waves traveling with different angles, each of which has this amplitude, and its complex valued amplitude. We'll have an amplitude in a phase, because of course, when we take the Fourier transform, we can end up with these components being complex valued. We can propagate each one of those plane waves. Yeah, we can find the path it takes, and we can write down an expression for that path, the phase accumulated by the plane wave. The intensities or amplitudes of the plane waves don't vary because of the eigenfunctions of plane space, of free space. And when we add all of these plane waves with the appropriate phase shifts due to propagating that distance together, we can find out the field and therefore the intensity in the output plane. And it turns out that if we're a very far distance away, we can show that over some limited region here in this plane, and for some limited region of angles per axial beams, the beams that are at a certain angle, and we're not worried about polarization at all, we've got our transmittance theory, and we can show that our output field is given by this expression here, multiplied by the Fourier transform of the input field with a suitable substitution for the spatial frequencies in here. So again, this is a effects of a Fourier transform, but again, we have to go back into meters. And so we take this Fourier transform, brings us to spatial frequency, but then we have to introduce this substitution so that we can talk here about centimeters in space. So our output intensity is a scaled factor of the magnitude squared of the Fourier transform. Yeah. Now, in the case of amplitude, so this now is illustrating what we do. This is what people do in optical signal processing. This is how they deal with these transmittance function. And this explains one of the simplest observations, the idea that I shine a laser beam onto a grating, and on the wall I see a set of spots. Okay. The plane waves, yeah, have been the output from that grating, and if it's a sinusoidal or cosinusoidal grating, are we've got coming out of it the field, which is simply the weak grating multiplied by the input plane wave. And at some distance away from that grating on the wall, we get the spots, which are effectively the Fourier transform of that grating profile. And if we have an amplitude grating, if we modulate the amplitude here, until we got a modulation factor of A, this is multiplied by the rectangular function. So we have a cosinusoidal variation in the amplitude, black and white. Then our Fourier transform gives us a set of diffraction orders, and these diffraction orders have shapes. Each spot has a shape like a sinc function, the Fourier transform, the rectangular edge. Yeah, this rectangular edge, this big thing in frequency domain is going to give us the smallest thing, the shape of the dots. And then the periodicity of the grating gives us a set of dots, and they're separated because the different plane waves are traveling at different angles. And this is what we get for our amplitude grating. And of course, the amplitude grating, the bad thing is that we're losing power. If we look at a phase grating, what we now have is we have an index modulation, which means that when we look at what comes out of that, the field at the output from that phase grating is going to be the phase of it is going to be modulated periodically. The phase will be modulated periodically. And if we go away and we do our mathematics, we end up with a transmittance function which looks like this. We have E, this is the effect of the grating, multiplied by the finite width of the window, rectangular function, where this A, this modulation now is a phase modulation, and it's related to our delta N, the variation in our effective index, multiplied by the distance through the layer, multiplied by beta, 2 pi over the wavelength, to give an optical path through this at every point. Yeah. And if we look at our far field diffraction, what we get is this. So again, we have our laser coming into our grating, and over at the wall, we get a whole series of these. And if we look at the amplitudes of these, we're going to see that the power in them will depend on these Bessel functions. So first order Bessel function and higher order Bessel functions. And we've got information, and this is quite important, both here and here. We've gone from the transmittance function to actually information about the power, the amount of power in each one of these diffraction orders. Now, previously we looked at the grating equation, and we looked at the Bragg equation, and we talked about the Evil diagram and representations of the effects of diffraction, either the diffraction due to the grating effect or the diffraction inside the volume. But now we've actually got a model which produces predictions about the intensity, okay, the intensity in free space, and can be linked directly into this idea of periodic absorption grating. So for example, the first gratings people would have used were doing Ronchi type periodic metal strips or wires that put around screws for astronomy, or phase gratings, patterned glass or scrapes on glass. This model, this very simple model, describes that behavior fairly well. Now, there are fundamental differences between the predictions for amplitude grating and phase gratings. Amplitude gratings, typically you cannot get the zero order beam to go to zero. You cannot get nothing transmitted and everything into the diffraction orders. And you're going to lose light due to the actual black strips in the on the glass. So the nature of the grating, that it's an absorption grating, means you lose light. And this is why in most cases people are not interested very much in absorption gratings anymore. And that's true also for volume holograms. Okay, but we have a good prediction for the distribution, the shape, and for the intensity in each one of the diffraction orders. On phase gratings, you can cause all of the zeroth order, you can stop the diffraction, everything being transmitted. And this you can follow here. You can actually find a value of A for which the zeroth order efficiency is 0. That's the first root here, the first 0 value here of this magnitude of the zeroth order Bessel function. And at that point, all of the radiation, if you assume this is perfectly lossless, no further reflections, all of the radiation is going to be in the diffraction orders, the higher diffraction orders. You also notice here that we have many diffraction orders. And again, this model, this transmission model, works well when we have big periods and we have low refractive index modulation. So this is archetypal thin grating. It's a thin grating. We typically operates on a very simple single scatter type of an idea. And again, if we look at this sort of behavior as we vary the A, and the A is associated with the thickness and the modulation, as we increase A, we get this sort of behavior and we get this scattering of the light, and we typically have the light spread out more and more between more and more diffraction orders. And we periodically see that we can make the zero order go to 0. And of course, we can make all the higher orders go to 0 as well at various points. But interestingly, we note that we can never get these diffraction orders to get close to 1. So we can never get a situation where all of the input light goes into one of the diffraction orders. And in fact, the +1 and -1 orders, the most we can get into those for this symmetric type case would be about 40% or so. Yeah. And again, if we change the angle of incidence, we're typically not going to see the pattern here will move. So if I tilt this down, so I'm coming up here, what's going to happen is the zeroth order is going to be up here now somewhere. This is going to move up, and all the others will be symmetric about it. But we won't see a lot of change in the intensities, certainly for relatively low angles. Now, this low angle I mentioned here is related also to this notion of paraxial optics, and the idea that we're assuming that pretty much all of these beams are traveling at relatively low angles, so we don't have to worry about Fresnel reflection and we don't have to worry about polarization effects. It turns out that you place these limits and you say, well, paraxial means ±10 degrees to the axis. It actually turns out that these models would work much better than that. They give you very good predictions up to sometimes much larger angles. It depends on the particular situation you're exploring. So this type of model, this type of discussion would very much tie in with this very first box here. Yeah. And as I said, any model we have any other model we have now is going to have to do better than that. And particularly, it's going to have to be able to deal with the smaller periods, the volume diffraction, the Bragg diffraction. Because as I said, this type of model is useful, very useful, and gives you very good insight into what's happening, but it has very serious limitations. Now, here we have a little figure, and I sort of tie this down here. And again, we mentioned before about thick and thin. I'm going to mention them again. But for thin gratings, it's multiple diffraction orders. It's thin. It's got a large period. we've got a range of parameters, and they're defined in SIMS, and I'm going to define them here as well. And I'm going to define them in the Kogelnik notation. Set of diffraction orders that you can define clearly as being thin, for which the model above would be a pretty good approximation, or for which you can introduce some Fresnel reflections and then make it an even better approximation. The grating equation here and the Bragg condition tell us about preferential directions and angles where diffraction orders can exist and where they can have this positive reconstruction, this multi-scatter reconstruction, but they don't tell us how much energy is in any of the diffraction orders. And in terms of this thin grating, we can write down this simple piece of mathematics here, where we have our complex transmittance function written as this Fourier series. We multiply our input field by that. We now have a Fourier series expressing this, and this Fourier series describes a set of plane waves. Okay, this is assuming that we have normal incidence, and we can use those things. I've got my dx in here, can give you the amplitudes, the power in each one of the diffraction orders. And our thick grating, we're going to typically have a smaller period, and therefore we're going to have very few plane waves outside the volume. And here we have a case where we've got 2 plane waves in the forward direction. And again, we haven't written any back reflection or anything like this. And again, the exact same parameters, which we're going to see, that we can use to define the thin, we can also use them to define that we have a thick grating. And again, in decoupling this notion of thick and thin from the actual physical thickness or thinness of the layer. And again, defining that for both cases, we have an average index, and then we have some cosinusoidal perturbation on the index. And this curve here shows this. This is just to remind you of this first order diffraction order for the thin grating, the Raman-Nath, this Fourier series type description, though the Raman-Nath we can actually write as coupled first order differential equations. But we have this general characteristic for the first diffraction orders, this Bessel function, the diffraction efficiency, the magnitude, the output intensity divided by the input intensity. This diffraction efficiency comes up here to a maximum, which is less than 40, around 40, and has this first order Bessel function, and twice it's going to be related to the coupling constant. But a Bragg grating, where we only have 2 orders, 2 plane waves, are going to have this sinusoidal type behavior. Now, again, we haven't derived that. I've mentioned it before, but I just want you to get used to this type of an idea. And this maximum diffraction into the first diffraction order can reach 1. So we can have 100% of the input beam put into the diffraction order theoretically. In the real world, we'll always have some boundary reflections. We'll always have some scatter in the system. We'll always have some absorption in the system. But theoretically, as a limit, if you're in the Bragg regime and you've got a thick grating, you can get up here. With a proper thickness and modulation, you can get up to 100%, whereas with the thin gratings, you're not going to get higher into a diffraction order than about 40%. And this again is illustrated here, and the formulas are written out. This here is our 2 characteristics, our sinusoid squared, our Bessel function. This here is this curve here, which is the plot between this nu, which is associated with the coupling constant times the thickness, and the K parameter down here, this Q parameter, which is related to this parameter here, the magnitude of the grating vector, the refractive index, the average, the beta squared, and the modulation. And we can actually write down that if this is less than 1, we're Raman-Nath, so we have multiple diffraction orders, and we've got weak scatter, we're not going to get more than 40% into a diffraction order. If we're in Bragg, we can get up to 100%. So if we've got a grating for which the ratio between these 2 parameters is greater than 20, we're in the Bragg regime. And then we have a whole series of intermediate regimes where basically we have some boundary conditions, or maybe not just 2 orders, maybe 3, maybe 4, where we don't have, it's not so simple. We're going to rely much more on numerical experiments, or numerical algorithms to describe intensities in this area. So we got good equations for intensity here, good expressions for intensity here, and not so good in here. And again, you may see this graph plotted as the log of this nu, this kappa d, against the log of q prime, in which case you actually get 2 lines. They basically cross here. You get 2 straight lines if you plot the log of this against the log of this, because of course the log of that parameter is the log of q prime plus the log of nu, and the log of this will be the log of q prime minus the log of nu. So you get these crossing axes. The other thing to point out, and again, we're going to derive out expressions so you'll be able to see this in more detail, but just to note that if we change the replay angle, so if we move away from the Bragg condition, we also get very different angular selectivity. And these are normalized graphs. These are the efficiency, the normalized efficiency. as we go, so they all have the same value diffraction in here, even though, as we said, the thin gratings won't go up to 100% efficiency. We just normalize them here so they all have the same value here in the center. And what you will see is that as you make the grating thicker, okay, as you make a thicker grating, so as you move deeper and deeper into this regime, the angular selectivity becomes narrower. So you only have to move a small angle to move off Bragg. Whereas you go to a thinner structure, something like this, what you're going to find out is it gets broader. So it becomes more selective, angularly selective, as you make thinner gratings. This would be specifically for transmission gratings. And as you make this thing thinner, you get less selectivity. So again, you don't have absolutely no selectivity, you have less diffraction efficiency, and you have less selectivity. Yeah, this tends to be the sort of characteristic. And you can characterize this. This is not as accurate as these parameters, but in some cases, if you're using exactly the same type of material, if you've got a thickness divided by the period greater than 10, you're becoming thin, excuse me, you're going thin, green. And if you've got a thickness which is less than, divided by the period which is less than 10, you're going to have effectively a thick type of regime. So basically, you're going to move towards a thicker region. And we'll talk about this because, of course, this is just observation. This is much more rigorous. This is based on the coupled equation. So this is really the formulas you want to use. And again, that's just drawn out here with the different regimes. And also, as I said, unfortunately, there are many different notations. And I've tried to indicate different notations that people use. Some people use Q sub G, some people use gamma, some people use this gamma here, and some people use nu. I will generally use nu because that's the notation that Kogelnik, and that's kappa D divided by the cosine of theta, the input angle inside the material. And kappa is your coupling constant, which is pi times N1, your modulation divided by the wavelength. And we'll talk about these a bit more later. But I think it's well worthwhile for you just to note this at this point. So again, we come back to our plane wave. Everything comes back in the plane wave. And particularly this now would refer to the notation that Kogelnik would have. We've got this plane wave. We've got an X and Z. We will use rho here. And rho is generally going to be what we talk about as the replay wave vector. It's got a magnitude which is beta. We're inside the volume now. We're talking about what's happening inside the volume. And we have an average index of n. And so we have a magnitude of this, which is 2 pi n over lambda 0. And so we can draw this in an eval diagram, which has got that as a radius. And here's our definition of our wavelength and of our two components of the wavelength. Here's our E field. We have an amplitude. Yeah. We have a propagation constant, and we've got a displacement or vector from the origin. And we can break this down and break it out then into simpler and simpler terms. And we've got our eval representation. And if we have a particular wavelength, we're going to have a particular beta value and a particular average index. And if we change this wavelength, the diameter of this circle changes. So as we make the wavelength smaller, because the circumference is related to 1 over the wavelength gets bigger. So this dotted line here, that corresponds to a wavelength less than lambda 0. And this one over here corresponds to a wavelength greater than lambda 0. So the bigger the wavelength that we use to replay, so lambda 0 will be our Bragg wavelength, our recording wavelength, the smaller this circle is going to become. The grating vector, the magnitude of the grating vector does not change. Once we record the grating, the magnitude of the grating vector is fixed. If we change our wavelength, we're changing the diameter of the circle, but we still have the same K vector if we're replaying that grating and representing it on the eval diagram. Okay? So this is our eval diagram. Again, repeat. Interference of two plane waves produce an interference pattern. The interference pattern has a certain period. We then put our sensitive material into that interference pattern right down here in the middle, and we record the grating. So we have this relationship between this K vector difference and the actual period or grating vector itself. And we can come along in this notation that Kogelnik used. Again, here's our two beams. They're not symmetric, so we're producing a slanted grating. Here's our angle of the grating. Yeah. Here's our Z direction. Here's our grating vector here. Here's our two plane waves. Here's our relationship here between the rho and the r. And here is going to be our K vector. And we note again here, we have a time. We expose for a certain time. We have a K parameter here associated with the material. And so we produce a modulation on our relative permittivity, which is proportional to the exposing intensity, the time you expose for, because of course you have the number of photons, the probability that they're going to be absorbed, and then you have some effect which is due to the actual materials. And this is something we'll talk about later. So that's our very basic, nice linear material description of the recording pattern. And here's our sinusoid. Here's our two beams. In this case, they're symmetric, so we have an unslanted volume grating. And here's our three-dimensional description with our thickness d in depth. And these nice period things which are perpendicular to the boundary. And now, one of the reasons we're very interested in this very simple transmission case is practical. If we have a material which shrinks or swells, okay, so the thickness increases or changes, then the transmission grating, the effects of that shrinking and swelling are minimized. So the shrinking and swelling will be associated with some change in the density of the material, but we might reduce, for example, refractive index at any location, but we've increased the D, and so we've kept the optical path length pretty much the same. We also have not changed the geometry of this object. On the other hand, if we have a slanted grating and we assume that the material changes, the thickness varies, so that this gets thicker, we're also going to have accompanied with that a change in the angle of these lines, these fringes. So in other words, our K vector, the direction will change slightly as we change the thickness. So shrinking and swelling for slanted gratings produces a change in the Bragg replay condition, whereas for the transmission grating, it does not. Which means that, for example, if we do experiments and we want to monitor what's happening inside the grating, we can set it up with a particular angle of incidence, and all the changes we see in our diffracted light are going to be due to things that have happened inside the material, as opposed to the shrinking and swelling, which has changed a change in the K vector. So we won't be moving for unslanted, we won't move off Bragg due to any swelling that takes place during exposure. So we have this idea of how a grating is formed. And we have this diagram here where we've got our two beams, our K vector, and our formulas, which show you what the K vector is equal to. And the particular case, 30 degrees, I think it's always nice to hang your hat on something that at 30 degrees, the period is equal to the wavelength, the exposing wavelength. You can always go back. It's like something that you just remember, and you can always use it as a reality check. And our evil diagram in this place, replayed on Bragg, we've got our input beam, we've got our K vector, and we've got our diffracted beam. So if we replay exactly on Bragg, this is what happens, okay? And again, we have an expression for our period. What happens when we change the wavelength? So we already talked about what happens when we change the wavelength. So here's our recording. Lambda is equal to the Bragg wavelength. We've got this nice K vector closure. Yeah, people refer to this as the closure of this vectors, this K vector closure. Yeah, and that's the closure. That is what Kogelnik uses to describe what's happening inside on Bragg. We have this very nice thing. We have an input beam touching the circle, and the K vector comes down here and touches the circle, and that tells us where our diffracted beam is going. If we change the wavelength, so I mean, if we make the wavelength bigger, the evil gets smaller. But the K vector doesn't change. The K vector is the thing that's inside there that's fixed. You recorded it. So what we see here is that for this particular K vector, if we try to replay it, if we take a row and we put it inside here, we're not going to be able to close this triangle. We will not be able to close this triangle. In fact, this is a fairly extreme case because we see that this dashed line here, the extent of the K vector, we have this situation where we're not even going to be able to get a K vector for the diffractive beam, which is going to be able to touch that circle. We're going to put in a beam, we've got our K vector, we're not going to be able to close the triangle on the circle, and in fact, we're going to have something very strange. We'll talk about that later. If we decrease the wavelength, our circle gets bigger, our K vector does not change. We can still replay on Bragg, and we can replay on Bragg by changing the replay angle. So we have changed our replay wavelength, and now we change the replay angle as well, and we can close this triangle. And this again comes back from all the maths we did, the mathematics with all the wave vectors. So we showed this is the case. We can replay on Bragg, and we can produce a diffraction order, and we can get very high diffraction efficiency here. In fact, we could even get 100% diffraction efficiency. So again, this is not telling us about the actual diffraction efficiency we get. We can't compare the diffraction efficiency for this case to this case from the evil diagram. But we do know that in both of these cases, we can satisfy the Bragg condition, and therefore we can have high diffraction efficiency. In this case, we pretty much know that we cannot in any real way satisfy the Bragg condition and produce high diffraction efficiency. We don't know exactly why or how, but we know we can't do that. We can also change our angle of incidence. So now what's happened is we keep the exact same wavelength as we had during the recording. And we change the angle of incidence. So here we have the nice Bragg replay. We've closed our triangle. And now we come over here and we use a smaller angle. And what happens is, in order to close the triangle, we have to take a diffraction order out to this point. Yeah. And on this case here, we've increased the angle. And what happens is we end up with a prediction for a k-vector, which is inside this. It's not touching the circle. So it turns out that in these two cases, we are off Bragg. Yeah. We are not satisfying Bragg conditions, but we can get diffraction efficiency. We can change our angle. And we set a little graph up here before. We just showed you an illustration where we said, oh, here's a situation. What happens between thick and thin when we change our angle of replay? Well, we say on Bragg, we get this nice diffraction efficiency, a maximum compared to all the other values. And as we change the angle, we stop diffracting as much light. We still have some diffracted, but we stop diffracting because we've moved off Bragg. So we go from a situation where we can make a grating and have 100% diffraction efficiency for that particular modulation, for that particular value of thickness. If we replay at the right wavelength to the right angle, we can have 100% diffraction efficiency. But then if we change the angle of replay, we're going to move off Bragg and we're going to have less light diffracted. So again, we're going to talk our way through the maths and we're going to explain this point by point. But if we can get all these little issues together and tie them all together, we should be fine. We have a very good understanding of what's going on. And we can link it up with the experimental values. Now, I introduced this parameter here. This is one of the parameters that's going to come out of our modeling. And it's an expression that Kogelnik has. And this is the parameter which tells you and quantifies how far off Bragg or if you're on Bragg. If you're on Bragg, this parameter is equal to 0. You can see beta squared minus the sigma squared. Sigma squared here is going to be the magnitude of the diffracted wave vector divided by 2 times beta. If the two of them, yeah, if the beta squared, if this sigma has that radius is equal to beta, so it touches the circle, then abracadabra, this is equal to 0 and you're on Bragg. And if it doesn't touch the circle, you're not on Bragg. One other thing I'll just mention here, we'll come back to this later, is that if I've got a vector here, and that vector, which is supposed to be a wave vector, doesn't touch the circle, that means that wave vector, which is equal to 2 pi divided by the wavelength, is not equal to beta. So we're going to talk about the field inside the grating, and we're going to talk about that field, how we can best represent that field inside the grating. And we're also actually going to describe the field inside the grating as being something, a plane wave associated with the input beam, with the same wavelength as the input beam. But it turns out you've got a flexibility, because all you want is a really good approximation to the E field, and you can do any trick, any mathematical trick you want to do that. It turns out that to get a good representation of the field inside the volume, you actually assume that you've got a plane wave with a slightly different wavelength. Now, this doesn't affect the wavelength of the light outside, and this is mathematics, yeah? But physically, we're interested in the field, not the individual plane waves inside the volume. And as long as we've got a good representation of that field, we don't care how we express that as the component plane waves, because we know the plane waves are not, in fact, modes inside the structure. So this is a little trick, and we're going to talk a little bit about that later as well. I just don't want
Professor Sheridan,
yes?
sorry to intervene. I'm
No
just
problem.
letting you know that the first hour of lecture is almost over, just about the timing.
Very good. So will we take ourselves a little break? People can go to the bathroom or have a little drink, and we'll start again in about 5 minutes. Or if you want, you can ask me questions. If people write in on chat, could I ask the moderator just to read it out to me? That might be the best.
Yes, of course. Sure.
And then, of course, if you want to, you know, like if there's a word you're not quite sure of, you could write it in Russian, and the moderator, I'm sure, has excellent English, so they'll be able to translate, just in case you're worried. Okay? So if anybody has any questions.
Professor Sheridan.
Yes.
I have a question on the complex transmittance slide. Like you said that we neglect, that we speak only about X component due to, like, just to simplify. And why do we neglect the Y component? Just because it is more, like, much smaller than the X one, or?
No. So in this case, our plane, our object is in the XY plane, okay? And we're not worried about anything that happens in Z, yeah? So if we want to, so we can apply exactly the same ideas to structures, to transmittance functions, which vary in X and Y, general structures. Could think of anything that has a variation in amplitude or phase in X and Y. In that case, we have to do a two-dimensional Fourier transform. Okay? So we'd have a T, so in this slide here I've got in front of me, this is, we'd have a T of X comma Y, yeah? And it would be equal to a sum, and you'd have a component Tmn, yeah? You'd have an M and an N, and you'd have an e to the plus j m times kx n times ky, okay? You'd have two integers. You could say maybe m and l, just to be clear. And then you'd express it in terms of components in x, kx, and also components in ky, okay? And what that would mean here is that this description here is for a one-dimensional structure variation. So that there is a grating where if I shine light on it, I would get a line of points on the surface. I would get a line of points. If you have got a two-dimensional grating and you shine a light on it and you look at the wall, yeah, then what you will see is you will see a two-dimensional array of dots. Okay? So now you have to tell me whether you understand or you don't understand.
No, I understood it, but is there any case when we do not neglect the Y component?
Oh yes. So I mean, in most cases, you do not neglect the Y component, because in most cases your grating is finite in X and Y. And so you would have to keep your rectangular function. Yeah. So your transmittance function would be the rectangular function multiplied by something. Okay. And in this case, we're assuming we have a periodic variation, and that periodic variation is only an X. So it would be as though we had a grating where our lines are like this. They're always parallel to the WY here. Yeah. But of course, we can have a grating where we have lines in X and in Y. In fact, we could have here a photograph. We could have the negative of a photograph. And if we shine light through that negative, we will get a diffraction pattern, but it won't be a very nice diffraction pattern. And then what we would have to do is describe that photograph as a Fourier series in X and Y. And then we would get a distribution in space in X and Y.
Oh, okay, thank you.
Yeah, very good. So here we have X and Y, and of course we can have plane waves. The plane waves I've shown here, this plane wave here is just traveling from here, but it's hitting this plane at that point. So in the case of a nice diffraction grating, all of the points would be along this X prime axis. But of course we can have plane waves coming out anywhere within this cone. We can have the plane waves coming out like this. Okay? Now again, all the EVOL diagrams I've drawn, these EVOL diagrams that I draw down here, they're all basically around this idea that we have a KX and a KZ component. But of course, yeah, X and Z, and here we have FX and FZ, yeah? But of course, we can have a sphere, an EVOL sphere. And in that case, we would have beams coming out in all various directions. So normally we're talking here about plane waves which are incident in the plane of the grating. We're going to talk about that, but we don't have to. We can change the angle of incidence. We can replay the grating in conical, what's called conical mount, okay? And we'll talk a little bit about that as well. But to talk about that, you have to be very careful about polarization. Is that okay?
Yeah, thank you.
Yeah. I mean, I strongly urge you, if you've got the opportunity to get a grating, there probably are loads of them in the lab, and maybe you can get one of the people in the lab to do this. Just take a grating, a nice line grating, and shine a laser beam through it and look at the spots on the wall, and then change the angle of incidence in the plane of the grating, so you see the line of dots moving up and down, and then change it in the perpendicular direction to the plane of the grating, and you'll see these dots then become curved. You have a curve arrangement of the dots. And if you look very close at the individual dots, depending on the type of grating you have, you'll see each dot has some structure. But if you've got, it will depend probably on the illumination, the shape of the illumination beam on the grating. Yeah, if you've got a Gaussian illumination beam and it doesn't fill up or doesn't illuminate the full grating, then those dots on the wall will look like Gaussians. Yeah. But if you've got a plane wave illuminating the full grating, then you might just about be able to see the sink-like behavior due to the rectangular window, because most of these gratings come not with a circular aperture, but with a rectangular aperture. I find that these sort of things really illuminate things for people. Yeah, you literally.
Okay, thank you. And may I ask you another question?
Sure, please.
It's kind of off topic, but you mentioned digital holography in the beginning of the lecture.
Yes.
And are there any requirements for the object to be recorded? And probably any requirements for the object to be recorded via off-axis holography?
Okay, so on axis, you're generally going to assume that your object, that the amount of light diffracted by the object is a small proportion of the total light incident. Yeah. So you don't generally assume that you put in 100% of the light and then the object scatters a lot of that light, more than 10%. Yeah, because otherwise you've got the issue of there being multiple scatter, complicated multiple scatter inside the object. So you're trying to look, once you get this field, you find out the field at the camera and you back propagate that field. So you can back propagate that field through free space to the top of the object, but often what people want to do is they want to propagate through the object. And if you've got a very complicated scattering inside the object, it's very hard to do that. It's very hard to find out information behind, okay? So that's one thing. This was the Gabor type system. So you've got all of the various orders on top of one another, and you've got to use tricks to eliminate those higher orders, okay? And then you've got to have a good algorithm to allow you to extract the phase. And this very nice arrangement. Another way to do things is if you've got pulsed light, you can, if you've got a fast camera or you fast detector, what you can do is you can try and synchronize the source and the detector. This is a different type of discussion, but it involves capturing only the light that comes through at the very, very beginning, because the light that has come through the very beginning of the pulse. So you synchronize the two, the pulse comes in, it's scattered by the object. So different parts of the light are delayed by different amounts of time. And if you only work with the first part of light that comes through, you can assume that light hasn't been scattered very much. And so you can extract out single scatter type information. In terms of off-axis, the big advantage of the off-axis is that you eliminate all these higher diffraction orders, all this confusing information that we talked about up here at the beginning. You eliminate all that order, so you don't have to get rid of the effects. If I can find where I talked about this at the very beginning, I think, where I talked about holography. Yeah. So on axis, all of these are on top of one another. Off axis, these beams are eliminated. You basically can spatial frequency, as part of your optical system, you can illuminate, you can remove them with the hardware. And so you can concentrate on just dealing with this. Online, you've actually got to find out some trick to get rid of these or to deal with these. So in general, off axis is better in terms of removing this noise, yeah, because these are noise terms and they can be very complex or confusing noise terms. On the other hand, off-axis can deal with much more strongly scattering objects. Yeah, you can effectively work with those objects, and also you have some changes in the spatial frequency resolution achievable by the two methods. Again, it depends on the size of the angle and the noisiness of the source. Unfortunately, there's never an exact answer. I'm sorry, you always have to qualify. But there are lots of nice papers out there that talk about these things, yeah?
And is there any limitation to the size of the object, like in digital holography?
Well, the first limitation is your size of your camera, yeah, and then the second limitation is your ability to position the camera accurately, yeah, stably. And then there are methods to increase your field of view using stitching. So what you can do, one method is to actually grab a couple of images, and of course there's going to be speckle in there. And then what you can do is, so images taken from different points in a plane, for example, or different perspectives. And what you do then is you do a correlation between the images and you align them, yeah? You find out where there's maximum correlation, and therefore you can stick the pictures together, and then you can process them as a single large picture. Do you understand what I mean?
Yeah, thank you.
Yeah. Now, again, it's once you start talking about computer algorithms, there are a million formulas because they're like recipes, and people claim advantages for different recipes in different situations. But that's a pretty good methodology. Slow, it can be slow, but you know. Is that okay?
Yeah, that's totally fine.
You're welcome. And again, we have here, this here is a nice figure because it shows these different orders. Yeah, the twin image, this digital reconstruction, and then the separation of the twin image away from the real image. Yeah, for an off-axis system. Yeah, so how you can cause them not to overlap. And you could do this actually inside the computer using numerics. Now, I haven't talked about things like deep learning. So you can train software to grab holographic images or holographic data and to extract out information using iterative techniques. And it can be based on calibration process, where you've actually trained the system on a number of previous captured images, or you can train it using a numerical simulation. So you can use numerical simulation to predict outputs and use those predicted outputs to train your system. So there's a lot of different things out there. And of course, just like ordinary imaging systems, you can fine tune the system, for example, by eliminating the point spread function of the system. So there's a lot of variations out there. Yeah, there's a lot of good research to be done by clever people like you guys. Okay. I'm too old to do research anymore now. I'm an old guy. Yeah. So we need young guys with lots of energy. Okay. Will I continue? Has everybody had the break?
So yes, I think there is no questions, and we can go on.
Okay. So we talked about off brag, and so again, just to show you, these were all off brag, on brag for unslanted, and just to show that you can do exactly the same type of constructions for slanted gratings. Here we have our transmission grating. So again, the two diffraction orders on the opposite side. And here we have a column dealing with reflection gratings where the diffracted order is on the same side as the input. And we've got next showing the K vector in the two cases and the evol diagram in the two cases. And this shows on brag replay for those two cases. Yeah, so space, spatial frequency. We can have off brag replay. So here's our off brag with the angle for slanted grating, and this is off brag again with the K vector closure for reflection grating. I've got two different lines here. I've got the red one here, which shows this K vector closure, which is the Kogelnik expression, the way he does it. And I've also got an other beam here, and this plane wave actually indicates more closely what you're going to see when you get outside the grating, assuming you were in a medium with the same refractive index. Okay, so the description of the E field uses these red beams in Kogelnik, but outside you're not going to change the wavelength. And in fact, this green distance here gives you information about how far off brag you are. And you don't have to use the Kogelnik expression for the E field. There are other expressions for the E field, and one of them is what's referred to as the beta value method, which was proposed by Okida, UCHIDA, a Japanese guy, and in many cases it actually works better than the Kogelnik method. So this is changing the angle, and this then is changing your wavelength and going off brag. And again, the both cases, the red for the K vector closure and the other one for the beta value. Okay. So again, just to give you a feeling for these things and how you can get information out of these evol diagrams and how useful they are to give you some idea or prediction of where the light's going to go. Okay, so we started off with the scalar model and we've talked bits and pieces with that. And now we're going to move up here to the Kogelnik type model. And this follows the paper. I gave you the reference and it's freely available on the web. And I strongly recommend you read it. Again, part of this is that everybody in the area reads Kogelnik. It's like our baseline. If you understand Kogelnik, and if you can then talk to other people in the area who work with Kogelnik. And I always love it to start with Maxwell's equations because they're such wonderful things. And there's a great sense of relief or steadiness about Maxwell's equations because they just have such wide and broad application. So here's our standard set of Maxwell's equations in the differential form. Divergence of the electric field density is equal to a charge density at a point. The divergence of the B is going to be equal to the 0. So there's no magnetic field sources or sinks. Divergence of D, we've got the E fields are sourced and synced to charges. We've got the curl of H is the rate of change of the electrical density plus the current density. And we have the curl of E is equal to the minus the rate of change of the B field, okay? And the first thing we always do is we assume something about the material. So we say we have no free charges. We have the relative permeability is equal to 1, so no magnetic effects effectively. We've got a relative permittivity and a relative conductivity. So this would be our phase, our index, and this is going to be absorption. And we make some assumptions, and we get down here to this wave equation, this Helmholtz type wave equation, where this k squared now is equal to this parameter here. So this is not just the phase constant, it has the phase term in here, but it also has an absorption term over here. Now in general, we're going to be interested in cases where this conductivity value is 0. We have no absorption or no loss in the material. We're going to retain it here. Kogelnik talks about both lossy and phase gratings. So we're going to retain it just like Kogelnik did. And it's worth noting that during exposure, we may have some absorption due to the dye. We mentioned this before, that the amount of light, the intensity in the material may vary with depth. But here we'll be talking about an average change in an average conductivity, which might vary with time. If we draw up an expression, here's our two-dimensional representation. Z is the thickness and X is here. Here's our sinusoidal interference pattern, and the sinusoidal interference pattern has produced a sinusoidal variation in our relative permittivity and refractive index. And then we're going to replay. And when we replay here, we've written it here very clearly that the E field here is pointing in the Y direction. So this here is supposed to be the end of an arrow, which is coming out of the page. And our H is perpendicular to the E. And of course, E cross H is going to give us our pointing vector. So in the 3D case, our E here is in the Y direction, and our H is up here perpendicular to the thing. We may have a HX component then. Yeah, so we have a component of the H field parallel to X. And we can write down our equations again. We can write down our material equations. We're going to assume that this field that's incident has a single frequency. It has a single frequency, so we can write in this phasor-like notation, e to the j omega t, where omega there is 2 pi times this temporal frequency, okay? And no free charge, and mu r is equal to 1. And we note here too from this diagram that that's our permittivity, it's k dot r, and the k vector here is along the x direction, yeah? It's along the x direction. So we have no ky component. There's no component of the vector in the y direction. If we talk about power here, we're only going to be talking about the power changes that happen as the waves travel in the z direction. If we don't say anything about the power traveling in the x direction or in the y direction. Ultimately, we're actually assuming that any power traveling in plus x or plus y, there's an equal and opposite amount traveling in minus x and minus y. Therefore, for a holographic grating, the general time-dependent vector wave equation, yeah, so we have something here as E is a function of X, Y, and Z, not a function of time, because we take care of our time here with this single frequency assumption. That's what it looks like, okay? So now we have this Laplacian operator, second order partial derivatives X, Y, and Z. We have this divergence, a gradient of a divergence, this here, and we have this term here, which depends on the permittivity and the conductivity inside the material, and this frequency, angular frequency. So that is what we derive out in terms of a general field has to be equal to 0 inside this medium. The hologram is assumed charge-free, yeah. And we look at our definition here of our field, and we see that the E field here is parallel to the fringes in the grating. It's parallel to them. And so if we look at our expression and we look at the divergence of the permittivity times the E field, the permittivity is a constant, yeah. Yeah. Sorry. we can say that's equal to 0 because when we expand this out, we get the divergence of E is equal to this, and therefore we're going to have this thing being equal to 0. So the E dot gradient of the permittivity is going to give you 0. So EY, IY is equal to E. It's assumed perpendicular to the gradient. Sorry, the divergence of the E field. Sorry, the gradient of the permittivity. Therefore, for TE polarization, this is equal to 0. And the wave equation becomes the following. So we have second order partial derivatives here. We've got some term here which expresses what happens inside the grating, and we've got the E field, that's equal to 0. For the lossless case, conductivity is going to be 0, and so this further simplifies to this form, where our EY, our single component now, we've got rid of the vectors. Our EY here is a function only of X and Z. So that's our governing equation starting off with Maxwell's equations. Now we haven't said anything about the form of EY yet, but that's going to be our governing equation for this lossless case. Weak cosinusoidal amplitude and phase gratings. Okay, again. So we're going to concentrate. This would be our description here, for example, if we had a permittivity variation. And this would be our description for our lossy grating. And we note here, this is actually very specific because we're assuming here that the conductivity is exactly in phase with the permittivity. Yeah. In general, we'd have to say this here, K dot R plus some phi. So we'd have some phase shift between them. But we haven't put that in here. It's not, we're going to typically be assuming that in fact our conductivity is going to be 0 in any case. Well, we have our governing equation. The K will have this general form. So now here we can see our cosine has become these two exponential forms with the K's. Where the beta is defined as before, this is the beta inside the material, so that's the average refractive index. We've got our N1 defined in terms of modulation, defined in terms of our modulation of permittivity and average permittivity. Again, we talked about this, how we go from permittivity to the refractive index. And we're assuming that the average index is much greater than the modulation. So even with the largest modulations we have today, we still have average refractive indices of 1.4, 1.5, and we've modulations which are 0.1, 0.2. So it's still reasonable. Our kappa now in this case, we're going to have a kappa term again, which is associated with the modulation. So we defined this, we talked a little bit about this earlier. It's associated with the coupling strength of the grating. We're also, if we've got a modulation of our absorptivity, we're also going to have that term in here. And as I said, we're going to generally be assuming that's 0 and this is 0 here. So we're going to be left with a term which is pi times the modulation, refractive index modulation divided by the wavelength. And again, the reference I've given you talk about this a little bit more. Now, if we had an actual phase term in here, if these two gratings were shifted with respect to one another, we'd have to have some relationship, some phase relationship between these two contributions to the coupling constant. So these gratings could act against one another. Okay, so our first order two-wave coupled wave theory, so this is Kogelnik. We're going to try and follow Kogelnik here. We assume an index in the grating of this form. This is our modulation. That's our total, that's the average. N0 is average, delta N is the modulation. Therefore, epsilon 0 is equal to N squared. The average permittivity is given by this. Yeah, it's the amplitude. Epsilon 0 is equal to this. We do outer expansion. And so we say that the modulation of the refractive index is approximately equal to this. Returning to the scalar theory, we can substitute in to the expression we derived above. We assume again we have no absorption. And we can do a little piece of maths. I do it step by step here because I think it's interesting to go through. And we use a beta here in 2 pi over the free space wavelength for delta n, and using the following variables. K0 is equal to beta times N0. So now that's our phase constant inside the material, which is an average index of N0. And kappa is equal to this, our coupling constant. We have the following relationship. This is our governing equation. And we've now expanded out our gradient to give our partial derivatives with respect to x, second order partial derivatives with respect to x and with respect to z. Our K0, and then our coupling constant, and this is a variation in x. So we have a variation here in x multiplied by the EY. So this is a slightly simplified form of the equation given by Kogelnik, but I think it's worthwhile just to go through this. And again, as I said, you should be looking at this with Kogelnik beside you. We can now go away again and we can draw out our evil diagram. And this is kind of useful here because we're going to have to make an assumption about the higher diffraction orders. So we're going to assume that we can describe what's happening inside the volume using two plane waves. So here's our Eva diagram, and we're on Bragg in this case. So there's our K vector, here's our replane diffracted order, but we can put an extra K term here, and we can put an extra K term down here. And we see that this K term here corresponds to rho plus K, and this term, the green one here, corresponds to sigma minus K. And we can see these are very far away from the circle. So they're very far off Bragg. Yeah. So what we can see is that if we do a calculation and we end up with these other terms, we can probably neglect them because they're probably not going to have an awful lot of the power because they're so far away from the evil circle. That's our argument. Theta b is the Bragg angle in the grating, and sine theta b is equal to K divided by 2 over beta n0. Again, you can derive this out from our basic fundamental ideas. And we can do little triangles and show everything. For the off-Bragg case, off-Bragg, we've got that the magnitude of the diffracted order is not equal to the radius of the circle, which is equal to beta times n0 or k0. And we can write out this diffraction order in this term. We can generate it using this closure, this vector closure, that we want to close the actual triangle. And so we see as we have the k0 sine theta, which is the input beam, and the k0 cosine theta, the input beam. But the difference is this minus K, and we've got this K is only in the X direction. So the difference between the two is going to be the input minus the K, and the K is only in the X direction. So we close our triangle, and whether we're on Bragg or off Bragg, this is going to be an expression for that sigma. And we show a particular example, for example, if we've changed our wavelength, for example. And again, I note here that this is longer than the radius of the circle. So we're actually assuming that inside the volume, we can best describe the field using these two vectors, an input beam and the diffracted beam, in which the diffracted beam has a different wavelength. It's not physical, it's mathematical. This is a strange result, as it implies that moving off Bragg in this way leads us to expect that a diffracted wave will have a different wavelength to the input light. This is a direct result of the use of the Floquet theorem, this closure of the triangle. For our E-field expansion, it only refers to the light inside the grating and to the wavelengths used to model or approximate the field inside the grating. Outside the grating, only the wavelength of the input light is measured. Yeah. Allowing for changes in index, and of course the frequency is always the same. The angle at which the diffracted order travels in the grating is also not that of the wave outside the grating. So we're saying we wanted to have a good approximation, and for mathematical reasons, we'll talk a little bit about this Floquet theorem now, but basically for mathematical reasons, we choose to have this strange way of describing the field inside when we go off Bragg, and it turns out that it's very useful. And again, as I said, this plane wave expansion, the plane waves are not modes. They're not eigenfunctions of this periodic structure inside the grating. Yeah. We're just doing some sort of an approximation. The waves outside the grating, inside the grating, are defined by the grating equation. So outside, we've already said what the plane waves are. They're defined by the grating equation. This change of angle must be allowed for before Snell's law allows for refractive index differences between the grating and the surrounding media. So we have to actually phase match the input field to the output field, which is what we do when we come to any boundary. So we express the field in a particular way, and then we match the field inside, the total field inside, to the total field outside to make sure to find out what goes across the boundary and what's reflected by the boundary. Floquet's theorem arose originally when people were solving equations for planetary orbits, elliptical planetary orbits. And they arose in the context of Matthew equation and Hill's equation. You can go away and look these up. And in good table books, they actually give tables of these things. Physically, it requires the E field in the grating to have a fundamental period, which is the same as the period of the grating structures. And the use of this expansion of the field in the grating is to define a set of Floquet block waves, or modes, in the structure. Okay, so we're talking about modes. Individual plane waves, like those we propagate in free space, do not physically exist. Okay, they're not independent. So they exchange. So plane waves, as they propagate through free space, do not exchange power. If you assume you've got plane waves inside a periodic structure, they will exchange power. Outside, they only accumulate phase. There are not solutions of the scalar wave equation inside the periodic structure. Modes are. Flow-K block waves are solutions of the differential equation, and individual modes can be excited and measured. A Flow-K block wave can be written as the sum of plane waves which beat together when a rigorous analysis is carried out. It can be shown that the coupled wave analysis is exactly equivalent to the modal when you've got an infinite number of beams. So a mode, you can excite a single mode inside the grating. Yeah, you can excite it just like you can excite a single mode in a multimode fiber, and you'll see that mode at the output of the fiber. In general, when we put light into a multimode fiber, the power is split between a series of modes. But the thing about each individual modes is that once power goes into the mode, it retains that power all along the fiber. The same thing here with the gratings. We're now using a plane waves. Those plane waves are going to be exchanging power, so they're not modes. Measurement results. Returning to the original strange result that off Bragg, one of the wavelengths, one of the gratings, or one of the beams that we're talking about has a different wavelength. Modes containing such components in strongly modulated gratings have been measured. So mathematically different expansions may be used and used successfully with different approximate assumptions. The plane waves are not eigenfunctions. They're not an orthonormal basis, if you want, for the actual speed field. The above discussion hopefully makes clear that it is important to ensure all the waves are traveling at the right angles and wavelengths in the correct medium. Okay, so we look at the steps again. The input beam must obey Snell's law at the first boundary. The wave vectors obey Flow-K's condition inside. So this one is equal to the input, the diffractive. The ith diffractive is the input plus I times k. Now this is not the grating equation, okay? Because this k can have components in the x and the z direction. But along the grating, it is, okay? At the second boundary, I have to be careful here, but once you phase match, it is. At the second boundary, the transmitted beam again obeys Snell's law. The diffracted beam, however, must be phase matched to the forward diffracted beam in the output. So you've got that this has got to be equal to this. The periodicity along the boundaries must be the same. It's basically what phase match. So in other words, they're locked in place in respect to time. A maximum on one side must correspond to a maximum on the other side. The equation becomes the following. And here's the actual description with N1, N0, and N3. X and Z, beam comes in, Snell's law, diffracted order due to the k vector, and then you've got the actual orders out here which obey the grating equation. Theta can be eliminated from the above equation, so the theta inside can be eliminated, yeah, to give an expression in free form all the angles of travel inside the grating. So this is our description for all the angles inside, and there's our I, giving the following relationship. This is the grating equation, which is true for all gratings. So this is the fundamental idea that happens, and this is the place where people either don't know about it or they get confused. And I emphasize this because this caused me a certain amount of difficulty when I started working with Kopernik. So we have an E field inside, we've got a two-wave expansion inside, and what we do is we have these two plane waves. So this describes the two plane waves, but we multiply each one of these terms by an amplitude which can vary as position in Z. And these amplitudes can be complex valued, and they will vary as a function of Z. So if these two plane waves propagating through the medium, which are multiplied by coefficients which are complex valued and vary with Z. And the Flow-K condition gives us this formula for our diffracted beam for the two components. And again, we're working here in X and Z, and here's the graphical explanation. And this here is our Flow-K condition specifically for this two beam approximation, where we have a rho associated with the input and a sigma associated with the diffracted beam. These are the propagation constants of what we call the R beam, and the S beam. This is the input, this is the diffracted. And we have this Kopernik works on this K vector closure idea, closing the triangle. So here's our K vector, here's our rho, and here's our closure between the two. What Kopernik assumes is that the E field in the grating can be written or described by two waves traveling in the grating. Energy is coupled back and forth between these two waves as they travel through the grating. Their amplitudes vary. Using Kopernik's coupled wave method, the wave equation is transferred into a pair of coupled differential equations. The waves are called the reference and the subject. And these two waves are assigned complex amplitudes, which vary the magnitude and the phase with the Z direction, the thickness in the grating. So we write our E field as a sum of these two plane waves with these complex position varying amplitudes. Rho and sigma are their propagation vectors and give the directions of propagation. They are related to each other by the flow K condition. And the K again is fixed 2 pi over the period in the X direction unslanted transmission grating. We change rho, angular wavelength, we will change sigma. And sigma is our diffracted direction. And again, with rho, we remind this is given by this and defined in these forms. So what happens? So what's going to happen is we're going to neglect all these higher orders. So I talked about these previously up here, got a whole set of diffraction orders. And I said to you, look, we're going to neglect those higher diffraction orders here. We're not going to worry about sigma minus K or rho plus K. We're only going to worry about these two here, which are added together to give you the K, the flow K condition. We neglect all higher orders. They're so far off Bragg, they don't contain any power. And if we do that, we're left only with the two beams, the rho and the sigma, the R and the S, and we plug those into the wave equation, and we're going to end up with two coupled second order differential equations. And I do this here, I write this out explicitly, substituting into the partial differential equations, we end up with 4 terms multiplied by these factors, and we neglect these 2 terms, and we end up with this multiplied by e to the j rho r, plus this multiplied by e to the j sigma r are equal to 0. And since these two things vary, and vary independently per se, we must write that for this to be equal to 0, this term has to be equal to 0, and this term have to be equal to 0 completely separately. The coefficients must separately be equal to 0. So we get 2 second order differential equations, and that's what we've got over here. And then we make an assumption about the second order derivatives. Yeah, we assume that those second order derivatives are negligible. They vary very, very slowly. So these second order derivatives are approximately equal to 0. And what we're doing is 2 things. When we assume that those are equal to 0 or negligible, we're assuming 2 things. The first thing we're going to assume is that we have this volume grating embedded in a medium. So if you'd like, the grating fills all space. And we're going to have a z equal to 0 plane and a z equal to d plane. And we're going to assume that we have some values of the s and the r at that plane, traveling in the forward direction. And given those 2 values at that plane, we're going to find out what comes out at this plane. And because this is perfectly grating fills all space, we don't have to worry anything about our boundary conditions. We can completely and utterly neglect the boundary conditions. So we don't have to worry about matching our E field and our H field. We can just assume values for the R and S components. But we're also assuming that the rate of coupling, the rate of change of the R and the S is slow. So we need an appreciable distance. Because we've got a weak modulation, we need to propagate an appreciable distance in order for the energy to be transferred. The light isn't jumping from one plane wave to the other in very short distances. It's a slow adiabatic process. So neglecting these second order derivatives means neglecting the boundary conditions and assuming a slow coupled process. And if we neglect those second order derivatives, and we divide across by the coefficients of the R, the first derivative of R and the first derivative of S, we end up with 2 first order coupled equations. So we have a first order R here, and we have first order S, but this R is coupled to S, and the S is coupled to the R. So we're going to get energy being transferred back and forth between the 2 of them. Now there's a number of other parameters here. These are called obliquity factors. They're associated with the fact that we can only talk about power and coupling associated with this propagation in the Z direction. I mentioned to you before, we don't say anything about transfers of energy in the X direction or the Y direction. We're only interested in things that happen in the Z direction. And so these obliquity factors make sure that we're only talking about coupling associated with propagation in the Z direction. And then we also met this previously before, which is this our off-Bragg parameter. If the beta, the sigma here, has the same radius as the evil diagram, then these cancel and this becomes 0. And if this becomes 0, this zeta parameter here becomes 0. And this is on Bragg, this is 0, and this is 0. So this is a measure, it appears here, it's a measure of how on Bragg or off Bragg we are. And we can see here it's a phase term, it's a coupling term, and we've still retained here this absorption effect, due to absorption, So if the second derivatives are retained, the two boundary conditions would not be sufficient. 4 would be necessary. Because we have to match the E field and H field about both the input and output boundary. And if we neglect the second order derivatives, we only need to know the amplitudes. Yeah. So the values of R and S at the boundaries. So if we match our total E fields, we need 4. In this case, we're only going to need 2. But also the H field would have to be matched across the two boundaries, Z equal to 0 and Z is equal to D. Mathematically, not only would there be 4 constants for the boundary conditions, but also 4 roots, as we're going to see, eigenvalues, yeah, values we need to form the solutions. And we're going to meet this a bit later. So we end up, in the lossless case, we end up with these two first coupled order equations. So we've ignored the loss, and we have this off-Bragg or dephasing parameter. Sometimes it's called the dephasing parameter, and the other parameter, the zeta, is referred to as the off-Bragg parameter, okay? So we talk about a dephasing parameter and an off-Bragg parameter. That's true to say. And the CR here, this obliquity factor, is associated with the input beam, and the CS here is associated with the actual diffracted beam. And we see here we have the K value here because we've got this change due to the coupling due to the grating. Okay, now, if we assume that the input angle is the Bragg angle, a perturbed version of the Bragg angle, yeah, so we're now talking about finding some little approximations. So if this, we moved away from Bragg by a very small amount, then of course we can say, well, the sine of that angle is going to be the sine of the Bragg angle plus delta theta times the cosine of the Bragg angle. And the sine of the angle is given by this, is defined by the grating parameters and the wavelength replay. So we can write down the sine of this new angle is given by this. And we know this, and we know this, so we have a linear perturbation on the sine, yeah? And we can go away and we can examine the off-Bragg parameter, and we can show that the off-Bragg parameter can also be written as a linear function of the change in angle. So this is just for very small variations away from Bragg. We note that. So if we're looking at perturbative, we can find out how stable it is, how much the diffraction efficiency will change if we go over a small angle. We can also take our differential equations and we can rewrite them. Yeah, we can change them. So here we've taken this formula here and we've taken this formula here. And what we've done is we've just taken this phase term inside here. So we've removed the dephasing parameter here from S. So we've come up here and we said, look, this is the S form here, but we've taken this and put it inside the first derivative. So we've removed that term and now we have two equations which look like this, where we've got a V now defined in the following way. So we can play around with these equations and find different forms. But one of the things we note here is that the effects of going off Bragg are like dephasing one of the plane waves with respect to the other. So they're not perfectly in resonance with respect to one another. We're actually dephasing one of the beams with respect to one another. We don't have optimal coupling. If the grating is replayed on Bragg, then we have this effect. And the differential equations they reduce down to this. So we've got rid of the off-Bragg term. And this is a first order derivatives equal to a constant times a function. First order derivatives equal to the same constant times the other function. So it's very symmetric here. We simply swap the S and the R. And we can take this and we can eliminate the S. And then we end up with a second order derivative equation in terms of R now, but we've eliminated the S. So previously you said this was very, very small, but now we're just saying, well, mathematically, this is completely consistent with what we have here. And we can say, well, we've seen this type of equation many, many times before, and we know the form of the solution for it. It's e to the gamma times z. And we're going to have a second order, so we're going to have a sum of two possible solutions. And we can substitute this in here, and we end up with the gamma squared plus that is equal to 0. Therefore, our gamma is going to have to be equal to plus or minus the square root of -1 times this. So there's two possible values, and therefore our form of solution must be of this form. R of z is equal to a constant times this plus a constant times this. For a transmission grating, the usual boundary conditions are that R at 0 is 1, so that's our input beam. It's got an amplitude of 1 at the input boundary, and S of 0 is equal to 0. We have no diffracted beam at the input boundary. The diffracted beam, or the power in the diffracted beam, is going to start to grow inside the grating, but initially it has no value, it's 0. Okay, and then we can come back up here to our figure and we can say, look here, this is coming in with 1, this is coming in here at 0, and then we have a transmitted beam and a diffracted beam. We want to find what those are. So we have the governing equation, we have the form of solution, Yeah, and we apply this condition to this when z is equal to 0, and we find out that the first derivative is going to be 0. We can come back over here and we can find that from here. If z is equal to 0, then s is 0, which means that the first order derivative of this must be equal to 0 at the boundary. So we know what the first order derivative is. We know what r is. R at 0 is 1. So we can solve our formula here. And if we do that, we find out that the R1 must be equal to R2 must be equal to a half. And R of Z is going to be given by the cosine of kappa, the coupling constant, divided by cosine theta times Z. And so this kappa divided by cosine theta multiplied by Z we call nu. Yeah. So that kappa is the coupling constant, and this nu here is the grating strength. And we can see that this starts off when Z is 0, this here is going to be the cosine of 0, which is 1. And as we increase Z, this is going to decrease until eventually it reaches 0. So as we make the grating thicker or stronger, we're going to get more and more light transferred from the input beam into the diffracted beam. Similarly, for the diffracted beam, we get the following formula. So when Z is 0, this starts off as 0. And as the grating gets thicker, the Z gets bigger, or the kappa gets bigger, the modulation gets bigger, we're going to get more and more of the light diffracted until eventually the cosine is 0 and the sine is 1. And then we're going to have the case of overmodulation where they start decreasing again. The solution of these first order constant coefficient coupled for the off-Bragg case differential equations is a simple matter. But what physically do the differential equations mean? The R and the S waves travel through the grating, energy is coupled backwards and forwards between them with the coupling constant by the grating. It's done slowly, and if the input is off Bragg, the dephasing parameter here increases, and the two waves are forced out of phase or out of synchronism with one another, and the interaction ceases or certainly decreases. The differential equation wave solutions of this form, put these into the differential equations, gives this solution, these equations, simultaneous equations, and these give a quadratic equation for these gamma values. This is in the off-Bragg case. So the previous case was on Bragg, and we got these nice simple values for these parameters, which we could use then in these expressions for R and S. But now we have retained, we've kept in the dephasing parameter, so we have a more complicated set of roots. And this boils down to this. This is our expressions. This is our gammas in the solutions. And these gammas have the following. We've got a quadratic equation. So we've got two roots. And of course, again, we note that if this dephasing parameter is 0, we simplify back down to the values we had before for on-Bragg replay. And we had the cosine and the sine for on-Bragg replay. Now we have more complicated solutions. Specifically for the diffracted, we get this parameter here, where this now is the dephasing parameter. And on Bragg, this is 0, and we're back to our sine. Yeah, and this is 0 here. We're back to S being a sine, and we square it. We've got a sine squared, and this obliquity factor is included here for the slanted case, off Bragg case, where basically we're not going to have the same angles. So we have to allow for the change in angles to talk about the power. Here's our coupling, the grating strength, and we've got D in here. We've got the off Bragg parameter with our dephasing parameter up here, and we get a diffraction efficiency, which is this multiplied by its complicated conjugate, the output diffracted divided by the input. Again, our definition of our diffraction intensity, the diffracted by the input. Unslanted transmission gratings, on Bragg, the angles are symmetric, and our S is equal to this, and our eta diffraction efficiency is sine squared. Okay, so I'm going to stop there now. We're about 10 minutes before the hour. So are there any questions about this? Again, I've tried to do this so that you can go to Kogelnik and see what Kogelnik says, but this fills in a lot of the gaps, the things that Kogelnik does not talk about, and works through them step by step. And I think starting off and working, and also the terminology, the evil diagrams and everything, working through this step by step is a good idea. Yeah? Is that okay? Any questions?
I wanted to ask, what materials can we read to get to know this topic better? So
I strongly recommend, yeah, for a number of reasons, but I strongly recommend those references I gave here. Yeah.
Okay.
So that book by Sims is a book. It's a very good book. and you can download it for free. Yeah,
Thank you.
and I've paralleled that quite a lot. The source of this though is Kogolnik, and that again can be downloaded for free. Yeah, Moram and Gaylord, it's very nice. They're engineers, and they talk about the rigorous models, which we're going to come to. Now there's a range of other books, and I'll bring other books just in case you've got stuff in the library that you want to go to. I'll bring some other books to your attention. They're quite nice books that are out there. I don't know if they're available on the web or not. I don't know really. But this is a very recent book, and it's by a man called Kostuk, and he writes, I think, quite well. And I'm going to refer to some of the stuff he did. And if it's in their library, you can get it. I don't know how much it is to buy new, probably a lot of money, okay? But all of these you should have access to, yeah? So Kogolnik is the oldest, then Moram and Gaylord, and then Sims. So the Kogolnik is 69, Moram and Gaylord is the 782, this paper, and there's several papers by them, some reviews. This is from the 90s, late 90s, early 90s, and this is from last year, 2 years ago. So that spreads a whole. But again, today I mentioned things that you could very, very usefully go away and look at on the web. Okay, and I have a great belief in going out and looking things up in Wikipedia to prime the pump to get you starting. Okay, and I mentioned these people: Lippmann, Bragg, Gabor. Okay, and then as I said, it's quite exciting because basically this next year is the 50th anniversary of Gabor's Nobel Prize, and the year after is the 60th anniversary of the work of Denisuk and Leithen Uputnik. Yeah, which I could imagine is a very big thing for your university, okay? So look these people up and you'll see photographs of them and you'll see descriptions of what they did, and it makes it much more alive, yeah? Much more interesting, I think. Okay? So any questions?
Professor, I have one more question.
Sure, sure.
At the slide 14.
Slide 14. This is up before this or today?
No, it's of today. Of today.
Of today. So just tell me when to stop. I'm sorry.
Yeah, okay.
This one?
No. It was much later. It was actually about the parameter K, which should be related to the material parameters.
Oh, so this is to do with the recording of the material.
Yeah. And my question is actually, what is actually the relation of this parameter to other material parameters?
So that I introduced that simply to illustrate going from, so I brought it in today, but I also brought it in previously. And it has to do with the fact that I've got an exposing interference pattern.
Yeah, here.
Yeah. So I have an exposing interference pattern. And I said, look, how do I get from the exposing interference pattern to this modulation of the permittivity and ultimately the refractive index for our cases? And I said, well, it's going to depend on the time, because if I expose longer, I'm going to get more light in a particular area. But we also have to take account of the fact that the material has some response. And if you go back previously, I talked about the old-fashioned way people thought about this, and particularly what they talked about in relation to photographic emulsions. So back here, I have a little figure that I just stuck in, and it was in the place where
it's about this beam ratio, right?
Yeah, it's about the it's here, okay? And I said, look, in the old days, particularly when people talked about emulsions, they would have talked about this type of characteristic, okay, where they would have had an exposure energy or a dose, okay, and they would have something which was like the response to material. So this figure is not now specifically about the beam ratio per se. This has to do with the exposure, the response, the TE curve for the film, yeah, the incident light exposure level. So in this case, you want to operate where the material is linear, okay? You really do. And what this is trying to say is that, look, I'm going to be turning this energy dose into something of modulation, yeah? And there's a region over which I can change that and I would get a linear response. And if I have too big of an interference fringe, or if I apply too big of a dose, so imagine we have an intensity which is varying sinusoidally, and then I multiply that by time. Okay, and imagine I've got maximum visibility. So I've got a point where the interference is 0. Well, as time goes bigger and bigger, basically what I'm going to do is I'm going to have a sinusoidal variation at dose where the value of dose at the maximum increases linearly with time. So if I have a nice linear material, yeah, and linear to the dose, then basically I'll have some average value, I have some sinusoidal modulation, and what I'm going to produce is a sinusoidal variation in permittivity or refractive index. Often this would have been actually the associated with maybe the absorptivity or the negative in the photographic emulsion. So what I'm assuming right now, and at the time when I talked about this, I also said, look, you know, we could very easily imagine that the response will also depend on the period of the sinusoidal interference pattern. Okay, so it wouldn't just depend on the dose, yeah, the maximum value, but it would also depend on the period of the interference pattern. So in real materials, it turns out that this is very complicated, okay? And not just complicated, so we use photopolymer, and you're going to work with photopolymer, and we're going to talk about the models associated with photopolymer. But it turns out that what happens in materials is much, much more complicated than the electromagnetic models. I like to start with the electromagnetic models because people think they're easy or they're complicated. In fact, the electromagnetic models are the simple part of this, because every material requires some slight different type of modeling. Yeah. Every time you change something in a material, you can have materials that you can record holograms in liquids. Okay. You can record them in plastics. You can record them in crystals. And the behavior, the material response in all these different type of media varies a huge amount. And the limits on the performance of these materials varies a huge amount. On the very lowest level, we talked about the light going into a material and there being a dye, and that dye absorbing the light. And that can lead to variations of the refractive index profile with depth, okay, by itself. And that's something associated with the response to the material because it's associated with the dye. You may have materials and you may have material in which you put light in, and for the first couple of seconds, nothing happens. You have an induction period. You will expose and you're waiting for something to happen and nothing happens. You don't get any grating for the first part of the exposure. And you can have situations where the absorptivity of the dye means that the place inside the volume where the maximum absorption is taking place varies within the volume. So there's a huge range of different types of effects that can happen. And all those effects I've talked about are just the dye. I've not talked about the mechanism that's actually happening. In many materials, there isn't a dye. So you may illuminate with a high energy radiation and cause changes in the chemical composition. You may break bonds, or you may cause a heating, which causes production of small cracks, yeah, or voids. So the actual variations in the functioning of materials, you have materials where illumination causes arms of polymers that have arms that have chemical branches that rotate. Okay, so you have many, many different mechanisms and many different models describing the different mechanisms that can happen in materials. So what happens in materials is pretty complicated. We're going to talk about relatively simple models that refer to polymers primarily, but I'll mention some of these things, and the books I've given talk about some of these issues in a far more detail than I'll have time or energy to talk about here. Okay?
Yeah, thank you.
You're welcome. Any other questions?
Yeah, Professor Sheridan, are those models that we have covered today, like rigorous couple wave theory and
we've
stuff?
Yeah. So today now, all we talked about was about the amplitude transmittance theory, and we talked about the Kogelnik. Yeah.
And
so we haven't actually talked about the rigorous model yet.
They are made for plane waves. And are there any theories that work for non-plane waves, spherical or cylindrical?
Yeah. So you can. So first of all, the main other class of models that have been produced for modal theories. Okay, where you talk about the modes inside the volume grating. And this is considered quite elegant, physically elegant, because of course the plane waves are the modes in free space. But if we talk about the modes inside the grating, each mode will be made up of many plane waves. okay? And the modes would, once their radiation goes into the mode, it would propagate through the structure and only accumulate phase. The amount of power in the mode wouldn't vary, okay? So a spherical wave is, so plane waves are representations of field and modes are representation of fields. And in free space, plane waves and spherical waves and cylindrical waves are all modes of free space. So if I put power into a plane wave or into a spherical wave or into a cylindrical wave, then it will propagate through free space and the amount of power in those waves will not change. And of course, I can express a spherical wave or a cylindrical wave as a spectrum of plane waves. Yeah. For example, a cylindrical wave is essentially a distribution of plane waves which has uniform power at all angles for all spatial frequencies. Okay, so you can go away and you can describe the field inside the volume grating in any way you see fit. Yeah, you can do that. The difficulty then becomes is it useful? Okay, is it actually useful? And one of the quite interesting things about the plane waves is that when we talked about the weak grating, the propagation of the fields in the paraxial approximation, in the low angle approximation. And the spherical wave or the cylindrical wave, by their definition, contain waves propagating in a whole range of angles. Yeah. So often if you're designing or you're discussing things in the paraxial approximation, it turns out to be quite handy to describe things or talk about things in terms of plane waves. So the answer is yes, you can use many different ways to describe the field inside the grating. Then you're going to have to phase match out of the volume grating into this free space. And then typically you're going to, at least in terms of modeling or first approximation, you're going to be talking about propagation through free space, often in the paraxial regime as a first guess. So by working backwards, you kind of see that, well, it's probably a good idea, since I'm going to work with plane waves anyways, outside, to work with plane waves inside. And since I'm talking about low angle plane waves outside, I probably don't need to use other types of approximations inside. However, if you have a structure, yeah, if you have a volume grating, if you record a volume grating and it turns out that you're, for example, making a lens and you're recording that lens with spherical waves, there may well be a good, there may be a computational advantage or an advantage in terms of insight by using spherical waves. I, off the top of my head, I can't think of anybody who's done that analysis, but it's a very good question. It's a little bit, it reminds me a little bit about the question about number systems. So you know we use the decimal systems, and the Babylonians used the hexadecimal, and of course computers use the binary system. And then the question becomes, which is the best system? Which is the best numerical system? Well, it turns out the decimal is pretty good for human beings, and binary is pretty good for computers, okay? And there are certainly particular cases where it would probably be very good to use hexadecimal. So for example, it was always said that people selling eggs, yeah, they would have a dozen eggs, and they could take that dozen eggs and they could sell them in pairs or in threes or in fours or in sixes. Yeah, there was many ways to subdivide in a neat way, which is why the hexadecimal, the base 60, is very useful, okay? But in general, they're equivalent. Okay?
Okay, I get it. Thank you. And I've got another question. Like you mentioned a couple of minutes ago about the linear, I don't know, not period, but when you've been talking about exposure, so there is some region of I don't know, material parameter that is suitable for recording sinusoidal grating, like to achieve sinusoidal modulation. And is it possible to achieve non-sinusoidal modulation on purpose? For example, I don't know, some rectangular or some other grating, but in volume?
Yes. Put simply, yes. And in fact, so if you think about, every system is nonlinear. Okay, if you take any system and you drive it hard enough, it becomes nonlinear. That's the simple answer. So you know, how would you record a square pattern? Well, it's very simple. Exposed by a very intense a beam, even a sinusoidal, very intense. And what will happen is you'll get saturation. So inside any material, yeah, if you expose more, you use up more of the material response. And if you expose hard enough, then basically you're going to use up all the response in a region and there's no more response left. So if you put in a sinusoid, it's, I think if you're familiar with the transistors, yeah, the response of all these devices is nonlinear. Every one of them, you've got a production of harmonics, and you try to limit the region you operate in over a finite region so that the higher harmonics are small, okay? Same thing with Hooke's law. If you take a rubber band and you pull it, you get a very nice relationship between the force and the extension. But any real rubber band, if you pull it enough, it's going to break, okay? And it's the same thing with these materials. If you expose with an intense enough sinusoidal pattern, you're actually going to produce a rectangular refractive index, yeah? Because you will saturate hard, yeah? So there are thresholds in the material. You have to put in a certain amount to get something to happen. And there are also saturations in the material. If you expose too long or too hard, you're going to get rectangular flat shape. Now, in most cases, you're not trying to do that, yeah? You're not trying to, you're trying to minimize distortion, yeah? So you're trying to produce a good facsimile. You don't want the distortion, yeah? So, but you can, yeah, you can certainly, you know, you want to make an art photograph, you want to have a good representation of the thing you're recording. But mostly it's about control. And if you understand the material, then you can control what you produce. So for example, you can expose with a more complicated pattern in order to record a simpler pattern, or you can expose with a simple pattern to produce a more complicated pattern. Okay?
Yes, okay, thank you.
Any other questions? Well, if there's no other questions.
So if nobody else has any questions to continue, I think it's time to actually thank Professor Sheridan for the lecture. Or does anybody?
So first of all, did everybody get the YouTube, and they have the YouTube available, yeah? From the last talk, yeah?
Yes, everybody should.
Okay, now I'm going to send you these slides. I'm going to send an email out with an attachment, okay? So you should be able to see that. As I said, it's a big file, and part of the reason I didn't send it out to you because I'm working on it. So I put new things into my slides this morning. So that's kind of the way I do this. I prefer to give it to you before the talk, but then you'll be seeing slides that you weren't actually before. So I'll give them to you. But I think as I said, there's only one thing I didn't like about the YouTube video, was that I think at least twice I called Denis Gabor Denizuk, which is pretty dumb, but you know, these things happen. Now, again, if you've got any questions, please send me emails. I note that there was one student who sent me an email, and that's really great, and we can have that discussion. I'm sorry, I'm very, very busy, so I mightn't be able to spend a huge amount of time. I've got another person in that university whose PhD review I've got to finish first before I start having fun and talking about scattering, okay? So please bear with me. But please feel free to contact me and ask me questions. Yeah, it's very interesting. Okay.
So then thanks everybody for the participation, and we are continuing, I guess, tomorrow.
Tomorrow. Yeah.
Yes. So
very good.
Thank you.
You're welcome. Cheerio.